In this video, we're going to be looking at topic 4b, crude oil, which is part of the IGCSE chemistry course from Edexcel, and we're going to be focusing on the single science outcomes. So what we need to know is that crude oil is a mixture of hydrocarbons. We're going to look at how we split crude oil into different fractions and look at the trends. We're going to discuss what is meant by a fuel and then what types of combustion we can get, so for a complete and incomplete combustion. And then looking at what happens when we have impurities in our hydrocarbons and then they are burned and what effect this has on the environment in terms of acid rain. So first of all, we're going to look at what is crude oil. So crude oil is a mixture of hydrocarbons with different chain lengths. So remember, hydrocarbons means they have hydrogen and carbon only. And they can have various different chain lengths. So you can have one carbon or you can have up to 100 carbons in the chain. It just depends, and it's a mixture and we don't necessarily know the composition. Now, crude oil is a finite resource. Remember, it is a fossil fuel. This means that it is non-renewable and we cannot actually replace it in the lifetime of a human. So we are using up fossil fuels very rapidly and we're not able to replace them. So eventually fossil fuels will run out. But in this case, what we're looking at is not so much what are the alternatives, we're looking at what we currently use it for. And it is made from the remains of ancient marine life. Now, when we're looking at hydrocarbons, in general, they have specific properties, regardless of whether they are an alkane, a cycloalkane, or so on. They will all have very similar properties, and this is due to the structure and the molecules that they're made up of. So what we see is that as we increase the chain, so as we add more and more carbons, we see an increase in the boiling point. So our boiling point increases, causing us to go from gases when we have short chains to liquids when we have medium chains, and then solids when we have long chain hydrocarbons. They also become less volatile, and this means that they're going to evaporate less easily. They become more viscous, meaning they don't flow as easily. So for example, if you're not sure what that means, if you compare water with honey is very viscous because when you try to pour it, it pours slowly, it's sticky, and it's not easily able to flow, whereas water pours very easily, so it is less viscous. We also see that the colour becomes darker and we get our flammability decreasing, meaning they don't catch fire as easily. And these properties all happen because of something known as intermolecular forces. And intermolecular forces are forces between the molecules. So this is nothing to do with the covalent bonds themselves within the hydrocarbons. It's to do with the bonds and the forces between the different molecules. And as these forces increase, when our carbon chain length is increasing, they become stronger and more difficult to overcome, usually meaning that we need more and more energy. So we can use these different properties to our advantage. One way that we use the properties to our advantage is in a process known as fractional distillation. So crude oil itself is a black, sticky substance that actually has no use. What we have to do is we have to separate it in order to get any sort of use from it, and we separate it into sections known as fractions. And the fractions are a mixture of different carbon chain lengths, but they'll be similar, so maybe 1 to 5 carbons, 6 to 10 carbons, and so on. And the reason that they are similar is because they are separated by their boiling points. So we take the mixture and we heat it, and it gives us the boiling points. And when they reach these boiling points and the temperature comes past them, they will then condense and we can collect them as a liquid. And this process is known as fractional distillation. Now, this is a very good link to show fractional distillation, and it explains it extremely well. It's from the Fuse School, and I will post this in the description below so that you can have a look at it. Now, this is a rough guide of what a fractional distillation column looks like. So what happens is, first of all, we heat the crude oil until it boils or becomes a vapour, and that is then passed in to the fractionating column. So this is the fractionating column here. And it's basically a huge column that has what's known as a temperature gradient. So you can see that we have a cool temperature at the top, which is about 25 degrees, and then it gets hotter as you go down and you get to about 350 degrees. And based on the different temperatures, what you'll find is the vapours come in and they will rise up the column because they're gases, and of course the gas particles are going to move quite easily. And as they reach a temperature where it's around their boiling point and then they condense back into a liquid, they are then collected in these trays, and then the trays are then coming out of the column and we can collect each of the different fractions. So it's separating it depending on its boiling point, and then we get this condensation. So that's here, we get condensation and collection. And you can see that we have the same trends that we just mentioned. So at the top, we get our small molecules. So a low boiling point, very volatile, flow very easily and ignite very easily. These tend to be gases. Whereas when we go to the bottom, we have very large molecules, very high boiling points, not very volatile, they don't flow and they don't ignite, and these will be almost solid. And there are a number of different fractions that we need to know. So we have refinery gases, we have petrol or gasoline, we have naphtha, but that's not covered too much in the IGCSE course, so we're just going to skip past that. We then have kerosene, diesel oil, fuel oil, and residue. So these ones, these 6, are the ones that you have to know as part of the IGCSE course, and you need to know the uses as well, and we'll look at them in just a minute. So just to recap, as we said, we have the crude oil being heated until it boils. The vapours pass into the fractionating column, which is cool at the top and hot at the bottom. And then depending on its boiling point, the hydrocarbon will travel up the column and then will be condensed and collected. So fractional distillation is based on the boiling point. So it's a key bit of information. It's separation based on the boiling point of each hydrocarbon, and then we can make a nice mixture. So we can look at the different uses of the fractions from fractional distillation. So if we start with the first one, we've got refinery gases. You can see that we have between 1 and 4 carbons. So these tend to be our small chain hydrocarbons. So these are going to have our low boiling point, they're very volatile, they're going to flow, and they're going to be able to ignite easily, which is why we use them for things like domestic heating and cooking. So natural gas, like we get from an oven or from a boiler, tend to be coming from refinery gases. Then if we move on to petrol, this is the one that most people will know, sometimes known as gasoline, and this is increasing between 7 and 9 carbons, and you can see the boiling point increasing as well, and this tends to be used in fuels for cars. Most of the time it's small cars, but you can get some large or SUV type cars that will run on petrol, but for fuel efficiency, some of the larger vehicles are more likely to run on diesel, which we'll cover in just a minute. Then we have kerosene, which is between 11 and 16 carbons. Again, slightly higher boiling point, and this is used again as a fuel, but this time we're looking at for a jet aircraft. So much larger mode of transport, needs quite a lot of energy, so we tend to use kerosene for the fuel, or we can use it as a heating oil for small lamps because it can burn and give off a nice amount of energy in the form of heat and light. Diesel is another fraction that you're probably very commonly aware of, and this is between 11 and 21 carbons. Again, we see the increase in the boiling point, and this tends to be used as a fuel for buses, lorries, cars and engines, or in general, your larger, more industrial vehicles will tend to use diesel because it's a more efficient fuel. A fuel oil has between 20 and 27 carbons, much higher boiling point again, between 350 and 450, and this is used as a fuel for ships or industrial heating, so heating very large spaces like a factory or a warehouse. And lastly, then we have bitumen, which is anything above 35 carbons. These tend to be solid and they have a boiling point above 500 degrees, and these tend to be used for road surfaces or for roofing. So it's important that we know the 6 main fractions and that we know the uses for each of them. It does come up as common exam questions. Now, we've mentioned fuels when we were looking at fractional distillation, and you'll have covered fuels back in Key Stage 3, but again, we want to just go into a little bit more detail. So a fuel is a substance that when it burns, it releases heat energy. So it gives off heat when we burn it. And the burning of fuels, or the fancy word for it, is known as combustion. And when we burn something, basically what we mean is we are igniting with oxygen. So we're reacting the fuel with oxygen, whether it's oxygen in the atmosphere or if we provide a pure oxygen supply, and this is a combustion reaction. And there are 2 types. There's complete combustion and incomplete combustion. You need to be able to identify the differences between the two and also write out an equation for each of them. So the complete combustion of all hydrocarbons, regardless of what family it's from, whether it's an alkane or an alkene, they will all form carbon dioxide and water every single time. And what we want to do is we want to then write out an equation to show this. So if I give you an example, we've got methane, which is a gas, and then we're going to react it with oxygen, which is also a gas, and we're going to form CO2, which is a gas, plus water, which is a liquid. Now, when we have any sort of chemical equation at GCSE, it is expected that we balance it, and hydrocarbons are actually the easiest to balance in terms of their combustion because you always follow the same steps. You balance the carbons first, then the hydrogens, and lastly the oxygens. So here I've got 1 carbon as my reactant and 1 carbon as my product, so that's fine. My hydrogens, I have 4 hydrogens in my reactants and only 2 in my products, so I need to make 2 waters. And then to work out the oxygens, all you do is add up how many oxygens you have on the product side and then divide it by 2, because oxygen is diatomic. So I have 4 oxygens in the products, I divide that by 2 and I get 2 oxygens as my reactants. So I can look at another example and I can look at octane, which is C8H18, and this is a liquid. When I burn it, of course, I'm reacting it with oxygen, and then this is going to form carbon dioxide plus water, and the water is a liquid, remembering our state symbols. So if I want to balance this out, I've got 8 carbons in my reactants, so I need 8 CO2s. I have got 18 hydrogens, but only 2 in my product, so I need to balance that out with a 9 waters. Then I can add up my number of oxygens and divide by 2. So I have 16 oxygens coming from the CO2, 9 oxygens coming from the water, so that gives me 25. If I divide that by 2, I get 12 and a half. But you can use a fraction when you have a diatomic molecule like oxygen. So you can have halves when you're using a diatomic. It's the only time that you're allowed to use it, and a half is the only fraction that you're allowed to use. Alternatively, if you don't feel comfortable with fractions, what you can do is a multiple. So you could multiply everything here by 2. So I make C8H18, but I have 2 of them, plus 25 oxygens to give me 16 carbon dioxides and 18 waters. They would be perfectly acceptable. Either one, if you're writing out a complete combustion reaction, is whichever one you are most comfortable with, just as long as your ratios are correct. So the second type of combustion that we can have is incomplete combustion, and this is when we have insufficient oxygen, meaning we don't have enough oxygen in order to fully burn our hydrocarbon. So therefore, we're at this time going to make carbon monoxide instead of carbon dioxide, but we will still make our water. So again, we can write out a chemical equation for this. So we've got methane, which is CH4, which is a gas, reacting with oxygen, which of course is still a gas. This time I'm making carbon monoxide, which is CO as a gas, and then H2O as a liquid. And of course I want to balance it because it is a chemical equation, and all chemical equations at GCSE must be balanced. So we have 1 carbon giving us 1 carbon, 4 carbons giving us 2, so I need to put a 2 in front of the water. And I do the same thing, I add up my number of oxygens, so I have 1 from the carbon monoxide, 2 from the water, that gives me 3, divide that by 2, and I would then make 1.5 oxygens. Or we could have it as 2 methanes, 3 oxygens, 2 carbon monoxides, and 4 waters if you want to get rid of the fraction. As long as your ratios are the same, that's fine. Now, the problem with incomplete combustion is this formation of carbon monoxide, as this is an extremely poisonous gas. And the reason that it is poisonous is because it binds to the hemoglobin that's in our blood. And you should know from biology that hemoglobin's job is to carry oxygen from our lungs and our bloodstream all the way around our body to all of the different cells so that they can undergo respiration and we can get energy and for the cells to be able to work. But carbon monoxide instead binds to the hemoglobin, stopping it from carrying oxygen. So it becomes an irreversible reaction. Once it binds, it cannot be unbound. So then by stopping the oxygen, it then starves our body of oxygen, so it can actually be fatal. It is a colourless gas, we can't smell it and we can't taste it. So what you tend to find is that a lot of places with the potential for incomplete combustion, like if you have a boiler, then they will have a carbon monoxide detector, and that will be an alarm that when it detects carbon monoxide, then it goes off because we don't want to be breathing it in at all. Now, the biggest problem with burning hydrocarbons, and especially when we have complete combustion, is that we make this carbon dioxide, which we know is a greenhouse gas. And we've discussed greenhouse gases back in topic 2C, gases of the atmosphere. So if you can't remember that, you might want to go and check out the video. And greenhouse gases are going to trap the heat that is radiated from the Earth's surface. So they stop the heat from going back out and being reflected into space, and it traps all in our atmosphere, and this can lead to climate change, which we know is a big problem. Now, not only can the burning of hydrocarbons cause climate change because of these greenhouse gases, it can also cause a phenomenon known as acid rain. Now, rain tends to be naturally acidic, around about 5.6 pH, roughly. However, if the pH drops below this, then we call it acid rain. And acid rain is formed when the water and the oxygen in the atmosphere reacts with either sulfur dioxide or even oxides of nitrogen that are then found in the atmosphere. And we get these gases being formed when we have impurities in our fossil fuels. So if our fossil fuels contain sulfur or nitrogen impurities and they are then burned, they will make these gases, and the gases can react with the water and the oxygen, and they form sulfuric acid and nitric acid, which makes then the rainwater much more acidic than it should be, and that can actually cause quite a lot of damage to various different parts of the environment, and we'll look at the effects in just a minute. So we can summarise this in various different equations. So if we've got sulfur, first of all, as our impurity, we're going to burn it. So this is our combustion. And in that combustion, we're going to form sulfur dioxide. So that gas is then released into the atmosphere, and it is then going to react with the water and the moisture in the atmosphere, and we can make two possible substances. We can either form sulfuric acid, which is H2SO4, or sulfurous acid, which is H2SO3. However, both of them still acidic, both of them can cause acid rain. Now, nitrogen, slightly different. We have our N2 reacting with our oxygen again in our combustion, and this time we're going to make nitrogen monoxide. But be aware that this same process can happen with any oxide of nitrogen. So it can happen with NO2 or N2O4 as well. They're the most common ones, but we've just kept it simple and kept it as nitrogen monoxide. It then reacts with not only the oxygen but also the water in the atmosphere, and we form nitric acid, which is HNO3. That dissolves into the rain, and then it falls as acid rain. So these are one of the biggest problems. As well as our climate change, we can get this acid rain forming. And acid rain can have negative effects on the environment and on ecosystems and just our general everyday life. Now, it's not a case of you will go outside during acid rain and you're going to get burned or anything like that. It's so diluted that it would not burn through your skin. What you may notice is if you are outside a lot doing a job that requires you to be out in the environment and you're in acid rain a lot, long-term effects could affect your skin, but short-term effects probably not. And to be honest, most of you have probably been outside in some form of acid rain and you just don't realise it. But the problem is when we have these long-term effects. So what can happen is we can get damage to marine life. So the acid rain can get into our rivers and lakes and it can cause the water to become more acidic. This could then harm the life that lives in there and it can even be fatal. It can also kill plants or trees. So again, they are going to be constantly being exposed to the elements and exposed to this acid rain, and long-term effects is it would start to eat away at the leaves and damage the roots when it gets into the soil, making the soil too acidic. Or we can even get limestone buildings. So limestone is a very common building material, both within the UK and the UAE and various different countries around the world. And when we get the acid rain falling on that, limestone is basically calcium carbonate. And when that reacts with an acid, it corrodes away and it can react, and we get this limestone being chipped away, and it can cause then damage to structures or damage to statues, various different things, and that can of course have a long-term effect because not only would we have to fix them, but it could cause potential human damage where a structure could become so unstable due to acid rain that it could then have to be demolished. So let's finish off by looking at some past paper questions. So this is quite a long question that covers various different parts of crude oil. So we're going to look at, first of all, the typical fractionating column being separated to separate our crude oil. And we want to name fraction A and fraction F. Well, we know that the top one, if you remember, is our refinery gases. And the bottom one, which has the highest boiling point, is going to be our bitumen. So that's our two different fractions there. And of course, we've got gasoline, kerosene, diesel, and fuel oil in the centre. So remember, as I said, it's very important that we do remember the 6 fractions and ideally in order. So most compounds in crude oil are hydrocarbons. State the meaning of this term. Standard question, always comes up, always worth 2 marks, and it is a molecule containing hydrogen and carbon only. And remember, you have to specify that it is only. And then we want to describe how the boiling point, the colour, the viscosity of the fuel oil fraction is different to that of the gasoline, and this is 3 marks. So you're going to get 1 mark per property. So if we go back, we can see that the fuel oil is lower than the gasoline. So we're going to be saying that, therefore, first of all, the fuel oil has a higher boiling point than the gasoline because it is lower down. They're going to be darker in colour because the colour gets darker as we go down the fractionating column, and the fuel oil being lower. And the last part is the viscosity. The fuel oil is going to be more viscous than the gasoline, which means it's going to flow less. So you could also say more viscous or flows less easily. Something like that to describe it. So 3 marks for just stating the 3 things. So higher boiling point, darker in colour, and more viscous. When hydrocarbons undergo incomplete combustion, a poisonous gas can form. So we want to state the condition that causes this, and it is insufficient oxygen. Or you can say lack of oxygen, not enough oxygen, oxygen not in excess. One thing to remember is it's not that there is no oxygen. If there is no oxygen, we can't do any combustion. It's that we don't have enough oxygen. And then the poisonous gas that is formed, that is carbon monoxide when it's incomplete combustion. And explaining why this is poisonous, it stops blood from carrying oxygen around the body. Now, you'll probably cover that in biology as well, and you can refer to hemoglobin and go into a bit more detail, but in chemistry we're just keeping it very simple, and we're simply saying that it stops the blood from carrying oxygen around the body. That's a suitable answer for chemistry. And then another problem with hydrocarbon fuels is the formation of substances that cause an environmental problem. And we can see that we've got some examples here. And we want to state the name of each of the products. So first of all, we've got SO2. So that is sulfur dioxide. And sometimes what can happen is the sulfur dioxide will then react with more oxygen to make SO3, which is sulfur trioxide. And then that sulfur trioxide can react with water, and then we will form sulfuric acid. So there are different ways that we can make this. We can either have the SO2 reacting with 2 moles of water, or we can have it reacting with the oxygen to form sulfur trioxide first. But it doesn't matter. In this case, we're simply looking for what are the names of each of these. And then describe one environmental problem caused by the H2SO4 formed. You can see that it's worth 2 marks, so it's not enough to just simply state acid rain. We're being asked to describe that. So the first mark would be to say acid rain, and then the second mark is to describe the effect. And you can be as detailed on this as you need, but you can keep it quite brief. So I'm going to just say that we get plants or trees are damaged or killed. Something like that, to say that you're going to be mentioning that the plants are being damaged, or the marine life is being damaged, or they were leaving the tip about the limestone being destroyed. But you want to focus on the environmental problem. So that's looking at the trees or the marine life. And again, just keeping it very, very basic, that they are damaged, they're killed, their growth is stunted, they're poisoned, harmed, anything like that. So there's the answers to the first few questions that we looked at. So looking at the fractional distillation column, what we meant by a hydrocarbon, and then the comparison, and then finishing off with the incomplete combustion and then the acid rain question. Now that's everything for the single outcomes for 4B crude oil. If you do have any questions, please feel free to leave a comment below, and we hope to see you back soon.